So in this video we're going to run through the exam questions related to rates of reaction for quiz 5. You should already have done the CC3 and CC4 revision questions, so this week is actually quite light. First reaction here, I mean that they give you lots and lots of information, but essentially this is what you're looking at down here. Circle the word that shows a change in rate of decomposition in each case. So if you made hydrogen peroxide more dilute, what's going to happen to the rate of the reaction? So they're talking about dilute. They're talking about how many particles you've actually got in the flask. Remember, in order for particles to react, they need to collide. If you've got lots of particles in a flask, they're more likely to collide. If they've got less particles, so if it's dilute, there's less particles in the flask, they're less likely to collide, and therefore the rate is going to be slower. The next one, the temperature used is lower. Okay, so temperature affects how quickly the particles move. If the temperature is high, they've got lots of energy, they move quickly, therefore they're more likely to collide. But in this case, the temperature is low. That means they're going to have less energy, they'll move slower, and they'll be less likely to collide. So again, that rate is going to be slower. If the reaction is carried out in a larger flask, I mean this one is a little bit trickier, but this isn't going to affect the rate of the reaction. You're still going to have, if you've got the same number of particles in there and you've got, it's working at the same temperature, so they're moving at the same speed, even if they're in a slightly larger flask, it's not going to change the rate of your reaction. Right, next one. You're asked to complete the diagram to show the apparatus to collect the gas produced. Okay, so remember, if you're trying to measure the rate of the reaction, you need change divided by the time. To work out the change in volume, you're going to have to actually collect the gas that's being produced, which is carbon dioxide, and you're going to do that in a gas syringe. And the important thing here is that it is sealed. So initially I'm just going to draw what is called a delivery tube coming out of the flask. Then I'm going to draw a gas syringe. I mean, it doesn't have to be a work of art. Just draw something that looks like a syringe. I mean, that would be fine. And then the really important bit here, the way I've drawn it at the moment, all the gas will be able to escape out the sides. So I need what's called a stopper or a bung to make sure that it's fully sealed and that no gas can escape out the side. Okay, now I would label this, that this is a gas syringe. And I would label this as a delivery, I mean you don't need all of these labels, this is a delivery tube. And I would even label here that this is sealed, or right bung, or right stopper, okay? Just make it super clear that there's no way a gas can escape out the side. Alright, the next one is a 6 marker. 6 markers on particle collision theory comes up all the time. Okay, so we're going to go through this one. Again, you're given lots and lots of information about this particular reaction. By all means, read through it. But I'm just going to come down here to the actual results box. And what you can see is that you're doing this reaction at 2 different concentrations. And you also have 2 different sized lumps. And in your question, you're asked to explain in terms of the collisions how the results show the effect of the size of the lumps and the effect of concentration. So there's 2 parts to this question. In one, I have to comment on how the size of the lumps affects the rate. In the other part of the question, I have to comment on how the concentration affects the rate. Okay, I'm going to start by just talking about the size of the lumps. Okay, and I'm just going to write size of lumps, and I'm going to write a paragraph just about that. Now when I want to talk about the size of the lumps, I've got small lumps and I've got large lumps. But you can see here I've got 4 different numbers because I've also got 2 different concentrations. That gets a little bit confusing. Because I only care about the size of the lumps, all I'm going to do is I'm just going to look at one concentration. Okay, so I'm just going to look at using 0.5, so the concentration stays the same. How is changing the size of the lumps affecting the rate of this reaction? You have to refer to the specific data in the question. So I'm just going to look at the top line and I'm going to say when concentration is 0.5, all right, and look what these numbers mean. 17.2 centimeters cubed of gas is produced with small lumps, and 3.1 centimeters cubed of gas is produced with large lumps. Now that I've quoted data for the table, I'm going to need to comment on what that data means. So I can see with small lumps, I'm getting more gas than with large lumps. If I'm getting more gas produced in the same amount of time, the rate of reaction is faster. So I can say, therefore, faster rate with the small lumps. So I've quoted data, I've explained what the data means, or I've said what the data means, but now I need to explain it. Why is there a faster rate with small lumps? I need to explain it in terms of collisions of particles. So I'll say small lumps have a larger surface area. You need to speak to me about surface area. Have a larger surface area, so there are more frequent, make sure you're using that word frequent, more frequent collisions. Okay, and that's it. That's all I need to write about size of lumps. In my next paragraph, I'm going to look at concentration. And again, with concentration, you can see, yes, you use two different concentrations, but you use two different size lumps. So again, it feels like there's a lot of information there. So I would just look at the small lumps. Okay, so I'm changing the concentration, but I'm not changing the size of the lumps. So I can see that at 0.5, I'm getting 17.2, but at 1, I'm getting 35.1. So I'm just going to again quote that. I'm going to say when small lumps, so I'm only using the small lumps, when small lumps are used, I'm getting 17.2 centimeters cubed of gas produced at 0.5 moles per decimeters cubed, and I'm getting that unit from here. And then I can say when someone to use 17.2 and 35.1 centimeters cubed of gas is produced at 1.0 moles per decimeters cubed. Okay, so I'm just talking about one size lumps, 17.2 if I use 0.5 and 35.1 if I use 1. So again, what's that telling me? That tells me when I have a greater concentration, I'm getting more gas produced, therefore the rate must be faster at a higher concentration. So I'm going to make that conclusion. Therefore, I've got a faster rate with a higher concentration. And then I need to explain in terms of particle collisions why. So I'm going to say a greater concentration means more particles per unit volume. And you have to say per unit volume. It means you've got more particles in the same area. So greater concentration means more particles per unit volume and more frequent collisions. More frequent collisions. Okay, if there's more particles in the space, they are more likely to collide with each other, therefore you're going to get a faster rate of reaction. Okay, so that will get you all 6 marks. Make sure you're talking about both factors, make sure you're quoting data from the table, you're explaining what that data means in terms of the rate, and then you're explaining why that change has the effect on the rate in terms of particle collisions. The next question here, why is the rate of reaction increases when the concentration of acid is increased? Okay, so we've seen that already in the question I've just answered. If you're increasing the concentration, you have got more particles per unit volume. That's the way we phrase this. Therefore, you have got more frequent, don't just say more frequent collisions. Okay, and there are your 2 marks there. The next one, another student suggests 4 other ways of increasing. Which one is correct? If you use the same acid but at a lower temperature, that's not going to increase the rate. Particles will move slower at a lower temperature. The rate will get lower. Using a larger trough, okay, that's not going to increase the rate. The size of the container is not going to have that effect. Using a smaller flask, again, using a different size flask isn't going to affect the rate. But this part here, using the metal, same metal but in powdered form. If you take the metal and you crush it into a powder, you are going to increase the surface area, and as we've just seen, an increased surface area leads to an increased rate of reaction. The next one here is in terms of particles, why reaction increases with temperature. Okay, so with temperature, you'll see that this is 3 marks, whereas when you were asked about concentration, it was 2. That's because you've got 2 distinct points that you need to make with temperature. The first point is if you increase temperature, the particles are going to move faster, and therefore they're going to collide more frequently. So that will get you 2 marks. Particles move faster, collide more frequently. But the other thing you can say is if you increase the temperature, that more particles will have the activation energy. So you get more successful collisions. And what I mean by that is the activation energy is essentially like the pass mark. And by increasing the temperature, you're giving particles more energy. It'd be like if I find a way to give you more marks in your quiz. If I gave you more marks, more of you would pass. If you give the particles more energy, more of them will have the activation energy, which is the minimum amount of energy they need to react, so more of them can react. So just watch how I phrase that. A lot of students will try and use the word activation energy in a sentence, and they'll misphrase it and it will make no sense. So it's on your carousel. Make sure you know how to use activation energy in a sentence. More particles will have activation energy, so you'll get more successful collisions. Okay. The next question you should have done already. It's in the previous video if you have not, but they're all the questions you need to do for this week on rates of reactions.